Hello and welcome to this tutorial on understanding a database schema. My name is Barry Williams. I'm a principal consultant with Database Answers. Let's start by establishing that a database schema can also be called a database design, a database diagram, or a data model. It's simply a diagram showing the tables or entities in the schema and the relationships between them. What you will learn in this tutorial includes how to understand the database schema, how a schema relates to the real world, and how a schema is built up step by step. The approach that we have adopted is to use two real-world scenarios. The first of these involves going into a coffee shop, placing an order, making payment, and taking delivery. From this simple scenario in a coffee shop, we'll progress to the second one, which is a more complex situation of buying a book from an online bookstore. In the course of this tutorial, I'll be explaining some very important basic concepts, and once you're familiar with these concepts, you'll be able to understand any database schema that you might look at, even if it's defined in a different notation. Now, these basic concepts include primary and foreign keys, one-to-many and many-to-many relationships, inheritance, and finally what's called rabbit's ears, or more formally recursive relationships. Let's begin by looking at the top-level schema that we will be examining in detail in the course of this tutorial. This diagram is an overview of our schema, and as you can see, it includes customers, deliveries, orders, products, and suppliers. We'll start by looking at a simple schema for a coffee shop and move on to a more complex one for an online bookstore. When we create a database schema, we might see many things that look like they might be in scope, but the schema itself will only include what we can call things of interest. For example, in a coffee shop, they sometimes make newspapers available free of charge. However, these are outside the scope of our study. In other words, they are not things of interest, and therefore in our database we will include only things of interest, which we can refer to simply as tables. I'd like to start by discussing some very fundamental concepts, the first one of which is a primary key. Now, every table in every database in the world has a primary key, and these are indicated in our diagram by a PK alongside the field in a table. They show the field that identifies the record uniquely, which is what makes them so important. For example, in our diagram, the product ID for a product is the unique field that tells you something about the product. The values are generally created by an auto-increment field, which is called an identity in SQL Server. These fields don't have any intrinsic meaning, and they're simply integers which are generated automatically, one after another. Foreign keys, which are indicated by FK alongside the field in a table, show a reference to the primary key for a record in another table. For example, in our diagram, the product type code in the products table is related to the product type code field in the reference products type table. In other words, there must be a record in the reference table for a valid product type to be used in the product table. We'll start in a simple way with this diagram, which shows two entities without a relationship. Let's say we go into a coffee shop to get a coffee and something to eat, or perhaps we're doing the office coffee run and we might have with us our order on a piece of paper. When we go into the coffee shop, they don't know us as a customer. Therefore, these two things of interest, products and customer orders, are not related until we give our order. Data modelers commonly describe a database schema as an entity relationship diagram, or ERD. This word relationship is therefore very important. However, at this point, we have established the things of interest, but we haven't established a relationship between them, and we'll do that in the next slide. one of the most important concepts in a database schema is that of a one-to-many relationship. These are very common in the real world and can be read as one parent can have many children. In this diagram, we can see that one product can be associated with many customer order products. The line between products and customer order products is a continuous line and not a dotted line. This means that the product ID field is a primary key in the customer order products table. A dotted line would indicate the existence of a foreign key, which we have discussed before. At the customer orders products end of the relationship, there's what's called a crow's feet symbol, which indicates the many aspect of the relationship. The little O immediately above the crow's feet shows that this is an optional relationship. In other words, not every product has an associated record in the customer orders products table. This applies, of course, to products that nobody orders. At the other end of the line, which shows the relationship, there is a small horizontal line. This means that at this end, the relationship is essential. In other words, every product ID in the customer orders products table must refer to a product ID in the products table. This means that the customer cannot order a product that doesn't exist. The line showing the relationship between customer orders and customer orders products shows a short horizontal line at each end. This indicates that every order must contain at least one product as a record in the customer orders products table. It also indicates that every order ID in the customer orders products table must match an order ID in the customer orders table. In other words, it must correspond to a valid order. At this point, I'd like to say a word about derived data using payments as an example. The total price that we have to pay for our order is derived from the total cost of the individual products that we've ordered. In a normalized database schema, we don't usually show derived fields such as total figures. One of the strengths of the relational database is that it requires us to strip away everything which is not basic and fundamental until we get to the point where we can't remove anything without losing meaning or content. For this reason, the total price is shown as a derived field in the customer orders table and is called DER_order price. This is a naming convention which helps us to clarify the point and emphasize the fact that we are breaking the rules to make the schema more understandable. At this point, I'd like to move on from the coffee shop to consider the scenario where we buy something from an online bookstore. In the coffee shop, we give very little information about ourselves as customers. In fact, if we pay by cash, we give no details at all. An online bookstore, of course, on the other hand, needs to know a good deal more about us. For example, they need to store details about our addresses, and we can have more than one of these. In our database schema, we could have a residential address, an office address, a billing address, and a delivery address. In passing, let me say that the existence of a separate addresses table is often a distinguishing characteristic between a database schema with limited scope and one which is intended for use in a mission-critical capacity. In our case, we store addresses in a separate table because it's a more general solution, instead of repeating address details many times in separate customer tables. This has many benefits. For example, it allows us to validate the address against files of recognized and valid addresses. This has become a standard approach, and there are many commercial products available to help us in this validation. In addition, maintaining a separate addresses table helps us in keeping track of changes in customer addresses. The primary key in the customer addresses table then becomes the combination of the customer ID, the address ID, and the date when the customer moved in. This works because, generally anyway, the customer cannot move into the same address more than once on the same date. Of course, they could move out and back in on another date, and our design covers that situation. This is another example where a many-to-many relationship can be found. In this case, a customer can have many addresses, and many customers can live at the same address. We resolve this many-to-many by an intermediate table shown in the diagram as customer addresses. Let me say a word about naming conventions. Good naming conventions can be very helpful in making any database schema easier to understand, especially if it's in an unusual or unconventional diagramming notation. Best practice in naming conventions recommends that the name of a table that resolves a many-to-many relationship should be named by combining the names of the two parent tables involved. So in this case, we have named customer addresses as a combination of the customers table and the addresses table. This diagram shows customers and payment methods, and in particular the fact that there is a many-to-many relationship which we have resolved with the customer's payment methods. Table. A customer can have many payment methods, such as different credit cards, as well as cash and check. And of course the same payment method can be used by many customers. You will notice that payment methods are considered reference data, and therefore in line with our best practice we have called that table Ref Payment Methods. You will also notice in the Customers Payment Methods table a field called Other Details. This allows us to, in the future, record details of such things as a customer's bank account without changing the underlying structure of the database schema, which is a very important design criterion to aim for. Let's move on now to the topic of products. As you might imagine, this can be a complex area. Two of the important aspects related to products are inheritance and product hierarchies. Starting with inheritance, if we look at this diagram, we can see a products table that holds details common to all products, a books table that holds details that are specific to books, and a coffee shop products table holding details for those products, are like children of the parent products table. Therefore, this concept is referred to as inheritance and is very powerful in the real world. On the diagram, it is shown by the circle with two short horizontal lines underneath it. Data modelers define these as subtypes of a supertype. At the physical level, in a database, inheritance can be implemented in one of three ways. The first way is to have three tables, exactly like the logical level. The second way is to have two tables, one for the bookstore and one for the coffee shop, with the common data items copied down from the parent table. And the third way, which is shown on this diagram, is to have one table at the higher level with all of the common data items and those for the bookstore and the coffee shop copied up into one large table. We come now to the second important concept related to products, and this is recursive product hierarchies. The line that comes out of the ref product type table in our diagram and then goes back in again is informally called a rabbit's ear, or more formally a recursive relationship, and it defines a product hierarchy. This means that any product can be part of a higher grouping of products such as categories, types, and so on. It's a very neat and powerful way to implement this concept. In our example, the parent product type code is a reference to the next highest level in the hierarchy, and of course the entry at that next highest level has another reference going upwards, and so on. There is also a recursive relationship defined for the products table, and this establishes the groupings within the specific products within the overall structure of the product type table. We have introduced suppliers in this diagram because the bookstore and the coffee shop are both suppliers of products within our schema, and this will be a starting point for a schema involving a more detailed analysis of suppliers, but the situation that we show here is adequate for our purposes. Finally, in our simple order processing system, we come to the stage of deliveries. Deliveries is a straightforward area to model in our database schema, and in fact we have added just 2 tables for this area. As you can see, a series of records can be stored in the customer orders delivery table. Each order will have a different date, and the date is part of the primary key as the order progresses through successive stages of delivery. For example, the order leaves the warehouse at one stage, clears the customs at another stage, another record but in the same table, and finally the order is delivered. This concludes our tutorial. This diagram shows an overview of the database schema, showing only the names of the tables and their relationships. It shows just the names of the important things of interest. This makes this diagram very useful when we want to discuss our schema with users, developers, managers, or any other interested party. It shows that products have suppliers and can be ordered by customers and delivered to addresses. In this tutorial we looked at the design of a typical database schema, and I hope that next time you look at a schema you should be comfortable understanding it, using it, and extending it.